Welcome to our video. We are Team Hawkeye from Buet. In this video, we will talk about our project, the Aerial Warrior. Hi everyone, I am Maisha Hawk, the team leader of Team Hawkeye. I think we will all agree in the recent years the weather has been extremely hot. In fact, the capital of our country, Dhaka, faced a temperature of 40.4 degrees Celsius in the month of April, which is the highest in 58 years. And it's not just about our country. Many other countries around the world, especially the South Asian countries, are facing the adverse effects of climate change. And just when we are suffering, there is one insect for which this extreme weather is perfect for surviving. It is our enemy, the Aedes aegypti, famous for spreading dengue in 129 countries, affecting millions of people worldwide. Now let's see how dengue is related to climate change. High temperature increases the reproductive capacity of Aedes mosquitoes, while heavy rainfall increases the survival rate of larvae.
Hello, I'm Asif Islam. Now we present to you the Aerial Warrior, a fully automated way to control dengue and save thousands of lives. You may have already heard of drones for dengue, and you may ask, what's the novelty here? Well, we have done some background study and we have found some major lackings. Our project not only contains any conventional drone, but the integration of full automation that does not require any ground control for object detection and actuation. The Aerial Warrior is an all-in-one project and has not been ever done before.
Hello, this is Sheikh Iftikhar Ahmed and I'll be explaining the database collection of this kind of dengue-prone regions and image processing part of our project.
One of the important parts of a project is to successfully detect the possible mosquito breeding regions through image processing. For this purpose, we have collected more than 1,000 of pictures by ourselves. These pictures are collected from households and university campus. We have used an online platform roboflow.com to manually annotate all the pictures of a dataset. After the annotation, we have applied several transformations like random flip and random rotation on our dataset for augmentation. After augmenting, the total number of images for training is nearly 3. We have used single state detection MobileNet version 2 TF Lite model. At first, we have built the model on TensorFlow. After the training, we have converted our model into TensorFlow Lite version because the Lite version is lightweight and more compatible to use in a Raspberry Pi. The overall detection accuracy of possible breeding regions is about 82.33%, which is very good for our project.
Hello, I am Omkon. I will be explaining the hardware parts of this drone. Look at this frame. We have used a 550 hexacopter drone frame, which is incorporated by 6 920 kV BLDC motor with 10-inch propeller. The heart of this drone is Big flight controller, which is connected with a GPS for automatic navigation. We have also connected a receiver if someone wants to control it manually. The code is run in Raspberry Pi 4B, which has a decent processing power. The drone is powered by 3500 mAh battery for a flight time of about 50 minutes. There is 2 laser sensors for obstacle avoidance and descent. We have built our own 3D printed display system with 3 nozzles for better accuracy, and the drone has other components like telemetry, buzzers, etc.
Our drone saves the GPS location of the detected dengue breeding object, and this data is used to map dengue risk zones.
We are also planning to use BTI, also known as Bacillus thuringiensis, which will kill Aedes larvae but will not harm any human or other living being.
The total cost for this project is about 57k BDT or around 550 USD. Cost can be reduced if produced in the industry. The model is scalable and we can scale it by accepting some trade-offs.
Let's see how the drone works in the real world. You can see the radio controller is on the ground as a proof of automation. The code is ran on the Raspberry Pi. A laptop can be used as a display for the Raspberry Pi so that the code runs in any remote device. When the code is executed, the drone takes off on its own. Then it travels slowly in a geofence which can be set by the code or the mission planner app. When a mosquito breeding zone is detected, then a certain interruption is generated and a command automatically tells the drone to descend. It descends until the height from the object is less than 120 cm. This is ensured by a laser sensor. After matching the altitude, it wears and dispenses medicine for a significant amount of time to make sure all the region is covered. At this time, the information about this point is also saved as longitude and latitude in a CSV file. After this, it resumes its mission. As you can see, the drone again goes to its previous height and continues scanning until the certain area or the geofence is covered. After covering this area, it lands automatically and notifies the user about its mission.
Initially, there was a query about how the drone will descend when it detects an object. At first, we proposed that the drone will descend 1 meter from the ground, but now we have improved that with the laser-based sensor. The drone comes down until the height is less than 120 cm above the detected object.
There is a query about obstacle avoidance. For this we have implemented two different methods. At first, if the obstacle is avoidable, then the drone changes its path to a new direction, and if the obstacle is not avoidable, then it lands to the ground. For our prototype, the obstacle avoidance is unidirectional, but it can be expanded in other directions.
Our project has a good market. From our country's perspective, some possible consumers would be our country's city corporation, and we have residential housing societies, autonomous corporation, and many others.
Thank you. That's all from Team Hawkeye.